Get started. Welcome to our second session of the USC AI Future Symposium on the theme of Will AIs Ever Be One of Us? I want to introduce the chair of this session on acting responsibly and ethically, Sven Koenig. Sven is a professor of computer science in the USC School of Engineering. Sven?
Thank you, Yolanda. So welcome to this session on acting responsibly and ethically. So it's basically the question of how can AIs do the right thing? And obviously that's a really important topic in AI these days. It's a topic that I'm very active in. It's also a topic that has many different facets and therefore needs to be attacked from many different directions. And therefore I'm very excited to tell you that USC has many experts on this topic, and we'll hear from some of them right now. So first up is Kristina Lerman. She was briefly introduced earlier. She's a principal scientist at USC ISI and a research professor of computer science at USC. Now, rather than introducing our speakers by their research interests, I'll introduce them by the title of one of the most highly cited papers. So one of the pieces of work that Kristina is very well known for is her work on the majority illusion in social networks. So today she'll talk about fair behaviors. Kristina.
Right, thank you, Sven. So good, next slide. Next slide, Yolanda. All right, so AI models have to learn. AI has to learn from behavioral data, often to learn to have predictive models. The behavioral data comes from very heterogeneous population. Usually comes from a heterogeneous population of humans, with people with all kinds of individual, inherent, personalized behaviors that we've been hearing earlier today in the previous keynotes. The behaviors that are motivated by their internal emotions, maybe some external events that are unforeseeable. Also, human data is really complex, really heterogeneous, really large and complicated, and within this data, the hidden relationships and confounders often introduce biases that pose threats to validity of the models that AI learns from this data. What kind of threats are these? Well, first of all, there's threats to predictions. Due to these biases and confounders, AI models that are learned will be non-generalizable and non-reproducible to other domains and settings, and will result in poor performance on held out data. These types of biases also pose threats to explanations. They might lead to lead scientists to make wrong or misleading inferences about individuals. This is what is known as ecological fallacy in science, where you cannot generalize to an individual based on group behaviors. And this, the real danger of this is that it will actually impact interventions. We might create wrong interventions to try to change behavior based on our faulty conclusions about how individuals act. And also it will create threats to fairness of the models. Models learned on biased data may actually entrench or amplify the same biases and discrimination that produced them in the first place. Next slide. No? Okay. So my work has actually addressed some of these biases to try to understand how we can mitigate for them. Some of the biases in behavioral data. So I'll talk I'll talk later on about Simpson's paradox. This is where subgroups within populations have different behavior, but in aggregate, different from the aggregate behavior in aggregate populations. I won't talk so much about sampling bias, but it is important because whenever you collect data, you might not actually have a representative sample of the population, which might mislead models. A very common bias is the survivor bias, where your characteristics of the population you're measuring are changing over the independent variable over which you're measuring those behaviors. Populations. And another new bias that recently become a focus of our work is aggregation bias. And I'll show you an example of it where it can create really faulty conclusions. Next slide. Okay, so this is one of my very favorite things to be studying. It's Simpson's paradox, which was first formulated in 1951. So if you actually kind of look at the slide, even though the illustration I'm giving is synthetic data, but it's very typical of a kind of behavioral data, social data you measure from people. If you squint your eyes and look just at the gray points. All social data looks like this, looks like a cloud of points. So you might look at the overall data. You look at the Simpson paradox states that the trend appears in overall data, but it can disappear or even reverse when the data is disaggregated by individual subgroups within it. So you see there's 3 subgroups that have negative trends in data, but unless you know about these subgroups, your algorithm, your simple, for example, regression models will see a positive trend. Next slide. Survivor bias is another important thing. So disaggregating, for example, in our work on stack exchange behavior, if you look at what is the probability that an answer in stack exchange is accepted as the best answer versus its position, whether it's first, second, or third answer that's written, you might observe a positive trend. But indeed, once you disaggregate by the session length, how many answers did the person write in a given session, the trend disappears. So this is called survivorship bias. Aggregation bias is another. We've been actually focusing on this a lot in different works. And whenever you aggregate data over time or maybe over space, as this one is showing, you might actually get really different conclusions. So here we were looking, just measuring the growth rate of COVID within different areas. And you see on the left, they're showing actually how the growth rate in the number of cases, infections of COVID infections within different counties within New York State. And you can do the same thing, actually aggregating or the counties to look at the state level information data. You can measure the growth rates, and those growth rates you measure in the state level will be systematically higher than the growth rates of COVID infections within individual counties. So this is the result of a special bias that's called aggregation bias, spatial aggregation bias. And there's similar ones that go in over time. Okay, next slide. And actually, what does it actually have to do also with, I mentioned that the biases can impact fairness. And this is a famous example here from, this was actually a court case that was argued in the Supreme Court, where people accused, the UC Berkeley was accused of discrimination in its graduate admissions because a smaller fraction of women were getting accepted to for graduate studies than of men. So overall, you see 35% of women were accepted to graduate studies compared to 43% of men. But once you disaggregate data by individual departments, you see that actually the situation changes. In most of the departments, here I'm showing just 6 of the departments, women actually have parity or even they have slightly advantaged for the higher fraction of female applicants are getting accepted for graduate studies to the school than men. Why does this bias exist? Well, it exists because if you look at department number 6, that is actually difficult for both genders to get into. More of the women applicants are applying to those departments that are hard for both men and women to get into. Whereas on the left-hand side, the departments that are easy for both genders to get into. That's where the very few women are applying to those departments. They're probably like STEM departments. So does bias exist against women? Yes, bias exists, but not in a fraction of applicants who are being admitted, but where the educational system, which departments they're being channeled in, because the ones that are hard for both genders to get in, those are departments on the right-hand side that are like, humanities, and the ones on the left-hand side that are easiest to get into are probably like STEM and engineering. Next slide. So I'm showing you that it is important to account for these hidden confounders and biases in data to understand this behavior. My work has been focusing on topics like how do you identify and measure biases in data? We have some code that can automatically discover them. We're also looking at how biases emerge in data and in social systems, in addition, including social networks. And then we're also looking at how do you mitigate biases in data. This is the new research area that's called fairness in AI. How do you, given that the data is biased, how do you learn models that do not bias or discriminate? So thank you very much.
Thank you, Kristina. We'll answer all of the questions at the end of the session. But if you have any questions for Kristina, please press the Q&A button now and enter your question. Next up is Fred Morstatter. He is a research lead at USC ISI and a research assistant professor of computer science at USC. One of the pieces of work that he is very well known for is comparing data from Twitter's streaming API with Twitter's firehose, asking the question whether the sample is good enough. And today he'll talk about cultural differences.
All right, yeah, so cultural differences are really important. If we don't have them, then we may make very erroneous decisions about a person's behavior or why it is that they're doing what they're doing. So first we have to define culture. So indeed, there are a lot of definitions for culture, but the one I prefer comes from Geertz. What Geertz says is that cultures are defined as a series of shared understandings among the members of that group. So these understandings can be things like what is good, what is bad, who belongs, who doesn't, and even like what is edible and what is not. And the cool thing about those is that these understandings manifest as redundancies in behavior. People adhere to them, and in their adherence, they do similar behaviors as others. This is particularly true in written text. So here we have a cartoon with real tweets from the Gamergate firestorm, where people were arguing about females' role in video game journalism. And there's a real opportunity for us here as computer scientists. So we can mine these redundancies in order to find groups and to understand what those groups stand for. So to color in some details about what I'm talking about, I'll go to the next slide. And this is some work we did where we were augmenting community detection. So in case you've ever played with a graph, you already know that when you draw the graph, there's going to be a huge component in the center and tons of these unconnected or lowly connected nodes on the periphery. And the first step for most people is they just throw these people away. They just throw those nodes out. They say, too little data, no use. But the problem there is that you are losing crucial information about certain beliefs in the population. So in the work that we did with Nina, what we did was we augmented a community detection approach to learn the membership rules for a particular group. And we applied those to the lowly connected nodes in order to incorporate them into our analysis. Why does this matter? We'll take a look at the slide on the table on the bottom right. So this shows how many hashtags are thrown away, about 40% across the board. But look at the examples. So Gamergate was about women's role in video game journalism. And these are some of the hashtags that are thrown away when you lose those lowly connected nodes. Things like ethics in journalism, feminist gate, misandric feminist. These are all important things that we would want to know, but we would be completely ignorant to them had we just lost those lowly connected people. As an aside, at the top we have this table. We show that we can first classify all of the users and a little more accurately than the state of the art. Next slide, please. So now I'm going to talk about some recent work that we've done with these shared understandings in the context of please go back one. In the context of software development. Yes, that's one fun. So we've been looking at this through the lens of something called Conway's Law. And what Conway's Law says is that any organization that designs a system, usually a software system, will produce a design whose structure is a copy of the organization's communication structure. And this has been reproduced time and time again for organizations. One example, McCormack 2012 found that tightly coupled organizations produce less modular software, and loosely coupled organizations produce more modular software. Again, the system reflects the communication structure. What we're asking here is, what about the influence of culture on the development of code? Here we're looking at country level culture. We're looking at the country from which the piece of software is developed. In order to do that, what we did is we collected GitHub repositories, all of them from 2017. We did some filtering. So, this is an AI symposium. So we focused on AI focused repositories. We looked at those for which we had the entire life of the repo captured, at least 50 events, 50 things happened, and in Python. That left us about 2,400 repos. And the geographic distribution of those repos is shown in that figure on the top left. You can see that the runaway winners in terms of frequency are both the US and China. So we looked for some differences in the way that people who make US repos and people who make Chinese repos interact. We found many differences. Just a few are shown here. So for example, the US repos have significantly longer comments. fewer forks, fewer issues, and fewer stars. So there's a difference in the way that the development process is carried out with US and Chinese repos. And of course, we ultimately threw these things into a classifier, and we were able to get an F1 score of 0.75. Next slide, please. So this is kind of an interesting case study of some of those repos. So we were looking at repos that come from companies that have a multinational presence. So all of these companies have offices in the US and China. We looked at their repositories and we took all of the measurements and did a PCA plot of them. If you don't know PCA, it's no big deal. The dimensions or the axes themselves don't carry a ton of information. What's more important here is to look at the actual positioning of the repos. So things that are closer to each other have more similar representations. And you can see that indeed there is some correspondence with organization and with the position. So those 10-cent repos are nicely put together. But what I didn't tell you is that that dashed line almost perfectly separates the Chinese and the US repos. So the ones beneath the line are almost all Chinese. The ones above it are almost all US. And what this seems to be showing is that actually the country of origin is outshadowing the actual organization even in terms of development. So there is definitely an effect of culture there. Next slide, please. So I'll go through this one pretty quickly. It's relatively preliminary. We're starting to go beyond just the actual repository activity and into the actual code itself. So we're looking at things like, hey, what do they import? Remember, it's all Python, so we can parse those pretty easily. And we're also looking at the actual code structure through things like ASTs. And some preliminary results seem to show that that's beating what we see in the repo level analysis. Next slide. So I just want to leave you on this note. So at the beginning, we talked about how culture is a series of shared understandings. And there's this taxonomy of such understandings that's really guided some of my thinking, and it may guide yours as well, and serve as kind of a nice launching off point if you're interested in working in this area. So this is the Burns taxonomy. They taxonomize the different types of rules that could describe a culture. Things like identity rules, membership rules, and so on. So that's a great resource. And that's all for me. Thank you very much for your time or attention.
Thank you, Fred. I noticed that there was a question for Kristina that sort of disappeared from the Q&A. If that was by mistake, please enter it again. Next
I
up
answered
is,
this in typing, so that's fine.
Okay. Next up is Shri Narayanan. He is a man of many talents. He is a professor of electrical and computer engineering, computer science, linguistics, psychology, neuroscience, pediatrics, and head and neck surgery at USC. He's also the university professor and Niki and Max Nikias chair in engineering. One of the pieces of work that he is really well known for is taught the detection of emotions in spoken dialogues. And today he will talk to us about inclusive design.
Thank you so much, Sven. So one of the running themes of developing human-centered AI that we are all talking about is how we can better lives through these technologies, especially with all the exciting advances that are happening across the whole ecosystem, from sensing and computing to data sharing. There's like new ways we can understand, support, and enhance human experiences, kinds of things that we saw in earlier talks like today from Sri Narayanan and so on. So therein lies a big challenge and an opportunity that these technologies that make AI that can become one of us, right, or in some way should work for everyone in all contexts. That is, it can handle rich diversity in who, what, where, how, when, and all these dimensions of sort of people and their interaction with one another and with the agents. So for example, let's consider an AI agent that can naturally interact with a human. Next slide, please. So let's play that video. So here what we're going to see is a parent and a child to create a story together.
Yeah.
Hold audio is not coming through.
Times B to be a line agent, to be a regular line agent.
Yeah, good job.
So if you can imagine for AI sort of systems to participate or contribute to such interactions, right? It needs to do understand these expressive behavioral interaction and respond in ways that's inclusive of all the participants, right? Understand the child as it understand a grown-up. Their sort of both their verbal and non-verbal behavior, what they're saying, how they're saying it, and so on. So next slide, please. So when you think about it, right, to sort of actually operationalize such a capability for these AI systems, we have to consider all these various elements from acquiring the data, analyzing it, understanding and interpreting it, and actually enabling the interaction in a human-centered way. And so this is actually very challenging, and sort of opens up a lot of questions. If you go to the next slide. There's rich sort of diversity and heterogeneity along many, many dimensions, starting with individual differences, right? Whether it is based on sort of demographic variables, age, gender, socio-cognitive abilities, language background, other health kind of states, the interaction type, whether two people are interacting or is it a small group, who are the interlocutors, what are the social registers, for example, are you interacting with a parent or a boss or with friends? Where is it happening? Is this interaction? What are the technology possibilities, right, that allow us to sort of, both capture and participate in such an interaction, just like we have our own sensory modalities. What kind of perception and processing abilities can AI systems have? In all this, right, we have to kind of make sure that these technologies are inclusive across this whole ecosystem from sensing and processing and interpretation and interaction, that they're inclusive for creating equitable experiences. So let me sort of illustrate that with a couple of examples. The next slide. So I'm going to draw examples from two domains just quickly. One from the domain of sort of behavioral machine intelligence, where the idea is to see if AI systems can participate in illuminating sort of human trait and mental states, and and perhaps support things in health applications, which is a domain that we work a lot in my lab. Mentioned. The second is trying to see how these inclusive technologies can in turn sort of be used for inclusion, in shining light on creating awareness about diversity and inclusion, for example, in the media. So next slide. And so hit one more time. We saw this example, child and parent trying to create a story together. So what are some of the challenges for making these technologies work for all, right? For example, it's well known that understanding child speech is far more challenging than for adult speech because of developmental changes. But on top of differences in physical, cognitive, socio-emotional dimensions. But on top of it, we can imagine health state differences, such as, for example, neurocognitive differences, such as in autism spectrum disorder. Then it presents further challenges for AI systems to be sort of being a part of supporting and being a part of these interactions. And so there's a lot of possibilities here in such domains for AI to be a part and support in understanding these expressive behavior interactions, such as, for example, turn-taking behavior. We saw examples from Alexa earlier this morning. Shared enjoyment, when people are laughing together. Well, should the sort of AI agent, understand and respond appropriately? Should the agent be polite? Some of the questions that Anthony Damasio raised about feelings and expressions of those. How should we make it happen? So to enable that, right, we need inclusion in how we understand and respond. The second example, next slide, please. So this is drawn from the domain of media, right? So we know media representations and portrayals are widely varied, and it's often people know that there is like unconscious or sometimes unconscious biases in terms of underrepresentation, stereotyping, and so on. And so the question is, once we are able to sort of, AI tools can inclusively sort of understand, people and their portrayals and representations, regardless of who they are, that can in turn shine light on these differences, right? Using inclusive tools for shining light on inclusion. So this is it's another project, example that we're working on to show how much, for example, female representation in film and television is, how our sort of representation in advertisements, how does it influence people's both experiences and behavior. So next slide, please. There are some results, right? So by using AI tools, right, to recognize who it is by computer vision, we saw talks earlier today about like audio processing, recognizing who what is saying, who's speaking when. We can actually compute very simple things like how much someone is seen and heard, and that can actually provide very interesting insights toward inclusion. Next slide, please. So, for example, looking at like you're from Los Angeles, film from the last several years, we can establish that like there's a sort of a bias in how much women are seen and heard in film, and that doesn't result to sort of the economics of how well these movies do in the box office. So women are heard and seen only about a third of the time compared to men. Likewise, another study that done in collaboration with Google showed that ads that had more parity in representation had more views. So again, these are sort of AI tools, right? Can help sort of shine light on some of these aspects, and there's lots more possible. To make this happen, right, we need to have technologies that are inclusive. So next slide, please. It's my last slide. So a lot of challenges, and which kind of point us to many opportunities for us to work on. Starting from we heard a lot about a lot of these models, and for AI depend on data, and getting the right data in natural representative settings and in right context is very important. Processing the data inclusively, understanding the variability and heterogeneity is important. We heard from Kristina about some of these sort of potential pitfalls and how we can begin to address them. And then finally, I think using the data and closing the loop with the various stakeholders, everything from data provenance and integrity to actually enabling the application of the data should be done in a sort of a closed loop manner, in which truly, if we want AI to be one of us, right, to be actually should be a partner in these kinds of adventures. So finally, so my closing slide. Next slide. So human-centered machine intelligence role. They help us do what sort of humans kind of know what to do, but also enable sort of new tools for offering insights that we haven't thought about, like for example, affect regulation, kind of connecting to what the keynote from Antonio Damasio talked about. How can we create tools that can begin to understand? So in summary, inclusion is central for creating digital experiences. Thank you. Listen.
Thank you very much. So next up is Keith Burghardt. He is a computer scientist at USC ISI. One of the pieces of work that he is really well known for is the myopia of crowds' cognitive load and cognitive and collective evaluation of answers on Stack Exchange. And today he will be talking about bias and opinions. Keith?
Great, thank you. Let me starting my timer. First, what I'm discussing is basically not just biases and opinions, but algorithmic biases and their effect on opinions. So essentially, collaborative filtering, crowdsourcing, and other such systems ultimately need data on human decisions in order to function. But there's a wide variety of biases in such data. For example, there's popularity bias, the preference for picking some item that's popular regardless of its quality. There's position bias, where you prefer something that's listed first. There's anchoring, where you sort of prefer a number that's large when you first see a large number. And then there's primacy, choosing the first thing that you see among many other biases. And the risk is that this creates sort of garbage in, garbage out. That if you feed bad data into algorithms, you create more biases, and you ultimately push your model away from what it was ultimately meant to optimize, which is finding better content and also reducing harm, reducing stereotypes and echo chambers and the like. Next slide, please. Thank you. So let me sort of summarize in more detail. What are the problems that algorithmic biases can create? Firstly, these models, because they reproduce past behavior, they're ultimately meant to, they're not meant to actually produce necessarily what you want, only what you've chosen in the past. And as such, they can, for example, enhance stereotypes. In the figure on your right, you see this person saying, when you Google unprofessional hairstyles for work, the unprofessional hairstyles that pop up are Black women with natural hair, while so-called professional hairstyles at work are simply white blonde women. Ultimately, as you see, it's just enhancing stereotypes that were initially fed into this model. But also, if you go back one slide, but also if you if you use these models, you can also increase echo chambers. For example, if you choose conspiratorial videos on YouTube, you'll be given options to view more conspiratorial videos, and you won't see necessarily a more complete picture. So seeing an item, really the issue is that seeing an item causes you to choose it, even when it's not necessarily something that you would want to see. Item quality can sometimes be secondary, and that's just due to biases. And what we'll focus on today will be item ranking. Next slide, please. So to better understand this work, I created a paper with a number of other collaborators, including Kristina Lerman, whom you heard earlier, called Origins of Algorithmic Instabilities in Crowdsourced Ranking, that was accepted and published at the CSCW conference last year. And the open problems we wanted to ask were, why is it that good items are not always ranked correctly? And also understanding ranking instability. Why is it that sometimes items that are in a given crowdsourcing system or collaborative filtering system can sometimes be chosen often and sometimes be ranked in very low down the system? So the goal was ultimately to model decisions and how people make decisions versus item quality and biases. So to do this, we created an experiment with 1,800 subjects where questions were given, such as the area ratio of the larger to smaller shape in the figure to the right. And there's an objective right or wrong answer, which are the two answers below that question. And we were given one of two options, which is in one condition, people would choose the answer, would choose an answer where you never knew what was the more popular answer. And in another condition, users were told that a randomly chosen answer was more popular. Next slide, please. So what that created was an opportunity to understand ultimately what was the effect of quality, what was the effect of decision biases, etc. So in an early paper by Seljanik et al. From 2006, what they found in this figure to the far left is that ranking is unstable due to what they initially thought was popularity, but also what was later understood to be position bias, that people would just prefer songs. In this case, they're trying to find the popularity of songs. They were preferring the songs that were listed first, regardless of how good the songs were. So when we created our model, we found that, when we created our experiment, we found that sometimes answers that were very obviously, one answer was very obviously better, that answer was more likely to get chosen. And in the middle figure, on either edge of that figure, that's what we ultimately see, that when one answer was much better than the other, that it was more likely to get chosen. But ultimately, when there's more ambiguity about what was the better answer, it was hard to figure out what was the, people would often make mistakes essentially. And so what we did was we created a model to fit this data. And we found first off that there was a strong bias due to social influence, but also we could very strongly understand what was why there was a sort of why errors were more likely to be had when the answers were more ambiguous. And what this model informed us was that about 20% of decisions were for reasons outside of quality, and that the other 80% of decisions are very error prone. The model also helped us understand that it was able to create a sort of phase diagram as a function of the relative answer quality and the position bias or social influence. And we find basically that if the answers are not much better or are not much better than each other, or that there's a strong social influence or position bias, you're going to get a whole lot of unstable ranking, instability in the ranking. But when one answer is clearly better than the other, the ranking actually becomes stable and the best answer floats to the top. And that helps explain in this early paper about 15 years ago by Seljanik et al. Why the best answers are still ranked at the top, in the very top right corner of the far left figure, and why the worst answers are ranked in the bottom, at the very far bottom left corner of the far left figure. And that where songs are more ambiguous, you get a lot more instability. Next slide, please. So ultimately, if you go back one. So ultimately, this helped us inform a method to reduce these biases and rank items correctly. And that's in the black line you see in the central figure. So what are our conclusions? Is that biases strongly affect crowdsourcing and collaborative filtering, and they propagate stereotypes and can enhance the echo chamber and polarize opinions, and that we developed a method to reduce these biases. And that there are several steps to address these biases, namely taking popularity with a grain of salt, that AI should not emulate humans, and that we need objective and diverse ground truths, which is what we produced in our experiment. So thank you.
Thank you, Keith. So our last speaker is Bistra Dilkina. She is an associate professor of computer science at USC and the co-director of the Center for AI and Society. One of the pieces of work that she is well known for is melding the data decisions pipeline, decision-focused learning for combinatorial optimization. And today she will talk to us about making good decisions. Bistra.
Thanks, Sven. Hi, everybody. Glad to switch gears a little bit and talk about the fact that one important consideration in acting responsibly is the way that we as AI researchers choose the problem domains that we focus our efforts on. And one of the grand challenges of the 21st century is sustainable development. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And in 2015, the UN established a broad set of sustainable development goals with specific targets and indicators that we as society are going to try to achieve by 2030. However, at the core of achieving these sustainable development goals is making informed decisions and actions. And this is where computer science, and in particular AI, can play a critical role in helping making those informed decisions and actions. In fact, in 2005, the new interdisciplinary field of computational sustainability was established as a call to arms, as a wake-up call, as a way to galvanize AI researchers to try to critically think and engage in trying to develop computational models, methods, and tools for sustainable development. So, in fact, next, please. Design of policies to manage limited resources for best impact, which is essentially what we have, limited resources to try to reach these sustainable development targets, translate into large-scale optimization and machine learning problems. So many of these fall in the realm of AI And in particular, I have focused on problems in the context of biodiversity conservation, disaster resilience, and public health and well-being. In fact, at the USC Center for AI in Society, our mission is indeed as a center to develop, test, iterate, and demonstrate how AI can be used to tackle the most difficult societal problems by a genuine partnership between computer scientists and social work and domain experts, and working closely with community partners to identify the real problems that are pressing, the data, the research methodology, and then work in evaluation and deployment of the AI models and techniques we develop in the field. Next, please. So today I want to just give you a glimpse of one of those domains, in particular disaster resilience. As you all know, natural disasters are increasing in scale and in frequency. In particular, flooding has a huge impact, and it accounts for 52% of the deaths from natural disasters in 2017. It has dramatic impacts on transportation, for example, as one of the lifeline infrastructures. Next. So one can ask, what are the best infrastructure upgrades that I can do a priori in terms of mitigation planning in order to maximize mobility during floods, maximize resilience to continue to operate as normal. The challenge in answering this question is the fact that we have limited budget, we have many possible subnetworks to upgrade, so combinatorial explosion, we have multiple resilience metrics, and we might need to, for example, predict what those mobility needs are. Next. And so we developed a data-driven framework for flood resilience road mitigation planning, where we leverage data on road infrastructure, such as OpenStreetMaps, hazard scenarios, such as the flood maps provided by FEMA, in order to compute the risk exposure of the infrastructure, such as the flooded road network, and combine that with mobility data in order to compute the actual impact, resilience impact of these natural disasters in terms of infeasible trips. Now, with all this in hand, we can think about how to optimize mitigation investments. Next. And so here we want to deploy an optimization algorithms to address this problem. We actually identified that this is a novel variant of the Steiner forest problem, and we show that in fact it exhibits an important structural property called restricted supermodularity, which then allowed us to develop a very scalable heuristic search algorithm in order to provide effective plans, the scale to the real world large transportation networks that we want to address. Next. So with this methodology, we were able to provide cost-benefit analysis that shows the resilience impact at different budget levels. And one important discovery here was that with very limited budget, but with the appropriate techniques to do strategic investments in the most effective places, we're able to give a big impact. With only 500 meters of road being fortified, we can recover 83% of the infeasible trips. So there is a big phase transition that will be not obvious unless you have this optimization technology at hand. And agencies, federal agencies like FEMA can really utilize these results in order to be able to provide, make decisions on federal grants that will allow local authorities to then implement these mitigation plans. Next. In fact, this flood resilience mitigation planning is even more critical in developing countries such as Senegal, which is an African country with pretty high flood risk. And in fact, our work on this domain started with the UN challenge called Data for Climate Action in 2017, where we proposed this formulation. And in fact, won the thematic awards for climate adaptation methodology. But the work here is not done. What we really need to consider is more resilience metrics in terms of, for example, access to critical locations, but also looking at how to optimize mitigation planning for equitable impacts by subpopulations. We want to make sure that the resilience improvements are balanced among different age, income, or geographic location groups. Next. One aspect that we observe here, as many other real-world domains that we work on, is this data-to-decision pipeline, in which we have data based on which observed data based on which we build predictive models that then feed into the to the decision algorithms that allow us to recommend policies and actions. And the traditional approach is really to take a two-stage approach where we decouple the machine learning aspect, which we try to maximize accuracy, and then feed those predictions as parameters into our decision making. The problem is that maximizing accuracy doesn't translate into maximizing decision quality when we have limited and noisy data. And in fact, all models are wrong, some are useful, and we want to find those useful ones, taking into account that what we really care about is making good decisions, having plans that in fact translate into effective impacts and outcomes. Next. So to address this challenge, we proposed the context of decision, the concept of decision-focused learning, where we want to automatically shape the machine learning model's loss by incorporating the discrete optimization problem into the training loop. So when we are training our predictive model, we're going to compute the loss based on what are the plans that we generate based on those predictions, and what are the quality of those plans with respect to the ground truth, which we have during training, and then use that as the loss that we back propagate. The technical challenge obviously is that propagating back feedback into the training process through discrete algorithms is very complex, and so deriving this kind of differentiable surrogates is quite a challenge. Next, please. So we have actually realized this decision-focused learning idea in the context of many discrete optimization problems, from linear programming and submodular minimization to clustering, mixed integer linear programming, and stackable games, and shown that it can provide quite beneficial outcomes. In particular, we have applied it in the context of improving tuberculosis treatment in India, where we showed that the decision-focused learning provided 15% improvement in outcomes compared to the classical two-stage approach. So with that, I would just like to conclude that I would really like to see more of the machine learning and constrained reasoning and search research in the AI community being inspired and leveraged to solve problems that are on the critical path to achieving the sustainable development goals that we have set for ourselves. Thank you.
Thank you, Bistra. So I want to encourage everybody to submit questions via the Q&A button. And I want to thank Cindy for having asked so many questions. And in particular, one of the questions that she asked specifically to one of the speakers, even though I think that this really can be answered by all of the speakers, is the following. We talked about lots of different techniques that utilize data. We talked about sources of bias detection in data, learning membership rules for groups, understanding expressive behavior, algorithmic bias in ranking, and decision-focused learning. And so all of these techniques that utilize data certainly have huge benefits, but dangers also loom. And Cindy wants to remind us that we as scientists have responsibilities here. So for example, she points out that the US has not adopted the general data protection regulations. And that means that users sort of automatically opt in by default to using their data rather than having to explicitly opt out. And so the question here is, what is it that we as scientists can do to support a responsible use of data? Who wants to weigh in?
I can start. Thank you so much. I think it's really bringing up very important points for discussion. The couple of points that I wanted to make in this flash talk, but I hope this discussion will also continue on to the panel that follows this set of presentations today. Precisely, pointing out both the promise and the pitfall, potential pitfalls of the various technologies of this whole ecosystem. So one of the things I wanted to point out is that this care, right, is broader than just in the algorithm side or when we are processing or decision making, but starts right from sort of where we are, who are we sort of trying to interact with, that includes the sensing and the data in an inclusive way, in a way that is sort of not just meaning it works for everyone, but also this consent and the data problems type of questions that were talked about earlier in the morning today that are important. But how these technologies are used and in what application context, there's not one shoe fit all, right? The mindful participatory way of thinking about, like, if we are developing AI systems to be sort of participate or as tools or sort of partners or collaborators in sort of in doing something together, then it has to be done in a very participatory way. Who are the people that we are interacting with? What kind of data, sort of protection, conditions, consent, all are involved, particularly in domains like health and so on, right? And this has to be thought about not as an after thought, but actually as a part of the design itself. Participatory approaches are well known and established. And this is something I think we all care about, but I'm sure like our colleagues here in this particular session have more to offer too. Thank you again for this question. I'm bringing up this discussion point, Cindy.
Do other people want to weigh in?
Yes, I guess I just say that I really appreciated what Wael said this morning about this, where we need to have ways to audit these types of things, and appreciate that every tool has a danger and kind of understand what that danger can be. And I think it's really important to do these things as early as possible, because you think about how long it's taken for example, climate change to be addressed, and we don't want to wait for this to become a problem before we actually do something. It already is a problem, as Wael would say.
Yeah, I would like to second that I think that this is Keith, in case you didn't see, that ultimately there's a limit to the benefit we can get from everyone's data, and there's a lot of false positives, etc., that can come from just collecting too much data. So there's a strong, it doesn't necessarily help us to collect this data, and it can obviously reduce privacy. So encouraging such work to improve privacy is for the best.
So maybe I can also quickly mention that AI researchers are now increasingly getting organized to address these kinds of problems on a variety of different levels. So for example, AAI, is one of the big professional organizations of AI researchers and professionals, is getting very active in that particular area. IEEE has launched a big initiative on how these systems should be designed. New conferences have been started, like the ACM, the AAI ACM conference on AI ethics and society. So I think Cindy is right that things need to get done. But lots of things are moving in that direction at this point.
I would like to point out we'll be discussing these issues, these questions on the panel later this afternoon.
Good, so we'll get back to them, which is really important since these questions are very important. I want to get to a question of Lauren. Again, it was a question to a specific panelist, but I think everybody can weigh in here. And the question is this. So we talked about processing lots of data. So what we are doing often is creating models. And one danger that looms here is that these models need to be interpreted, right? If they can't be understood by humans, then lots of dangers loom. And so here's the question of how can we ensure this? How can we build explanation facilities for the systems that we are creating so that humans can understand what is going on inside of these systems and intervene if necessary? Who wants to weigh in?
I guess I could weigh in first. So I think this is very important, especially working with practitioners, and the subfield of kind of explainability in ML has gained a lot of pace and velocity because the issue is so pressing. And I believe people are really putting effort in trying to understand what methodologies we can deliver in order to provide explainability, either as a core kind of characteristic of the approach, or as a tool that we can use on top of maybe more complex black box models. And I guess creating trust and understanding is an important way of catching possible problems with model bias and so on. I would argue that beyond explainability, one should just also have this whole idea of evaluating our models for fairness and equitability as such a core aspect of developing models that it becomes almost like unit testing in software development. Literally, we want to start building this into our somehow basic fundamentals of AI, where anytime we develop a model, we also run it through a complete analysis and stress testing for possible, undesired behavior. Now, in terms of ML, there's been a lot of progress. I would say that the biggest challenge that is looming wide open is how do you provide explanations for optimization for plans, right? So you have, let's say, computed this complex mitigation plan, which is an effect of this, big network with interacting components, and within all of those constraints that you need to consider, something comes out as the optimum. How do you explain to the people that might receive that plan why is that the optimum? It's very hard, and I think a lot more needs to be done on that aspect, explaining the outputs of optimization models rather than machine learning ones.
Can I weigh in? This is Kristina Lerman. I think actually we tend to, as computer scientists, we tend to think this is a technological problem. This is a computer science problem. We can solve it with algorithms or just building better models. But I think we also need to consider the human component, and we cannot solve it without people. For example, many of the algorithms, maybe even in the optimization space and many other algorithms, have unintended consequences. You cannot foresee what kind of consequences they may have if you don't know what to watch out for. And unless we have inclusion and diversity among the scientists and the programmers who are creating these algorithms, we will not know what kind of unintended consequences we should be on the lookout for. And then we won't be able to prevent them. So I think in addition to explanation, which is very worthy goal, we also need to strive towards diversity and inclusion among the people who are creating all these algorithms. That's why I'm seeing what recent events on Google, for example, kind of offer a hope for that we are on the right track, trying to, we will write ourselves and go on the right track to trying to bring more inclusion eventually to computer science.
Anybody else? Perfect. That allows us to end right on time. So I want to thank the speakers again. I want to thank the audience. And the next session is coming up.
Thank you, Sven, and thank you to everybody. We are going to take a break, and the next session will be in 15 minutes. So at 30 past the hour, it will be 1:30 p.m. Pacific, and we'll hope to see you all there.